First of all, I would like to acknowledge the organizing committee to give me the opportunity to present our work. So I am come from Paris, and I am in the CNRS laboratory. And in my group, we try to do some work in electrochemistry, for instance, for energy storage application. Here the, oops. Okay. During my talk, I will show you an overview of activity of my group, and after that, I try to define how to use redox active ionic liquid for electrochemical energy storage. And I will take the example of a redox flow lithium-ion battery, and I will finish by some conclusion. Okay. In my group, in fact, my group is some multidisciplinary group. And our main activity is to combine electrochemistry and bioengineering to do two kinds of application. In fact, one of the target of activity of my group is energy application, and other one is bioenergy. And here the idea is to develop the different kind of materials or nanomaterials to investigate the electrochemical or photoelectrochemical property. But in the same time, we try to develop some ionic liquid, particularly the task-specific ionic liquid, and you use this for some energy storage application, but also some bioengineering application. We are able to how to modify some surface by grafting some ionic liquid, and in this case, it is possible to control and to modulate the property of the interface. So, okay. Briefly, what is ionic liquid? Maybe some people are not familiar with ionic liquid, but ionic liquid is that it's a combination of some anion and cation, and some of them are organic compounds. The main interest of ionic liquid is that it is a molten salt at ambient temperature, and it is possible to modulate the property of the ionic liquid by changing the chemical nature of the cation or the anion. In this case, you are able to control different kinds of property. Basically, one of the main properties of ionic liquid is that they are negligible vapor pressure. From electrochemical point of view, they are a large electrochemical window, but by means of some simple chemistry, it is possible to tune the properties such as the balance, hydrophilic and hydrophilic balance. It is possible to change the design of ionic liquid to modify the solubility, and also the thing is that we can tune different kinds of property. So our strategy is that we do many work based on by using imidazolium unit, and the idea is that to use some simple chemistry to introduce some functional group. And here, for example, we just some basic chemistry. And the idea is that depending upon the functional group we want to analyze, we can tune the property. And we develop some task-specific ionic liquid, mainly for surface modification, for energy storage system, but also for different kinds of biological application. And however, the main one drawback of ionic liquid is that it's very expensive. But for electrochemical application, it is more interesting to immobilize this ionic liquid at the interface, and in this case, we have exactly the same property as in by using ionic liquid as a solvent. Because in fact, ionic liquid can be used as solvent, but also as supporting electrolyte. And sometimes it is possible to have some functional group. And here, our strategy is that we try to develop different kind of methodology, how to immobilize this ionic liquid, this redox active ionic liquid by means of covalent bonding. Why covalent bonding? Because in this case, we can obtain a stable system, and for application point of view, it's more interesting. So, this kind of ionic liquid can be used for different kinds of application. I will show one example about this. As you know, for example, in the field of electrochemical energy storage, that we have supercap and battery. The main difference between supercap and battery is that in the case of supercap, they are huge power, but low energy. On the other hand, battery can have high energy, but low power. So the idea is that if we can if we are able to design some specific ionic liquid, and in this case, we can obtain high energy by using some redox active system, but also if we are able to improve the kinetics, we can improve the power. And in this case, what we are doing, we are designing some specific molecules, mainly a new family of redox active ionic liquid called redox active polymer ionic liquid. And in this case, we can combine the property of supercap and battery, and we obtain a new kind of new family of electrochemical energy storage that can be called the supercap battery. And here the idea is that by means of some molecular design and some electrochemical investigation, we are able to not only to optimize the energy that can be stored, but also to improve the kinetics. So just an example here, for example, in this case of system, with this kind of system, we can do some polymer, nanostructured polymer, wherein some positively charged imidazolium. Here we have a ferrocene, as just for an example of some compound can be oxidized, and anthraquinone. In this kind of system, it is possible to oxidize the metallocene group, and also we can able to reduce the anthraquinone group. So the same compound can be used as in the case of organic battery. But the presence of this positively charged imidazolium improves also the double layer, the capacitance, the double layer at the interface. And here, for example, when you show the cyclic voltammetry of this kind of system, you can see here the redox peak, here for the anthraquinone, here for the ferrocene, and between we are mainly the capacitive response. And in this case, we have analyzed and optimized and show that this kind of system, when it is immobilized in nanostructured surface, mainly in 3D material, a 3D electrode, for example, we can obtain a huge energy, but also high power. It's just a prototype, but we can design different kind of metallocene, but also some organic compound. And here the idea is that by choosing carefully the design, the combination of the anode part and the cathode part, it is possible to improve the voltage that can be obtained in this kind of system. Another kind of hybrid system that we developed also is the combination of redox flow battery and lithium-ion battery. Why? In fact, as you know, for example, in the case of redox flow battery, that can be useful, for example, to store some renewable energy. The maximum energy that can be stored depends upon the concentration of the electrolyte that we can store in the tank. So, in fact, the solubility of some electroactive system that can be stored in energy in the tank is limited. So the idea is that, okay, we try to replace this electroactive compound by using some well-known materials that can be used in lithium-ion battery. And in this case, the idea is to, by the combination of the marriage of a redox flow battery and lithium-ion battery, we can obtain some redox flow ion battery. And here, the main idea is that it is possible to improve not only the energy density, but also we can obtain some safe devices. And here the idea is that, okay, when we try to investigate this new kind of system, and today I will focus on the kinetics of the charging of discharging of one active materials. And to do this, we use the concept of redox targeting compound system. Basically, for example, it's just some scheme, at lab scheme. For example, here we use titanium dioxide as anode and lithium iron phosphate as cathode. And the idea is that we need some redox couple that can be used for charging or discharging the materials. And one recommendation is that the formal potential of active materials that store the energy in the tank should be in the middle of the redox peak of the redox shuttle. So, okay, based on this thermodynamic consideration, now we want to investigate the kinetic part. So to do this, we use scanning electrochemical microscopy because this kind of electrochemical techniques allow us, for example, to investigate some local reaction, and in this case, we can determine some kinetic parameters for the charging and discharging of the iron phosphate. Basically, how the basic principle of scanning electrochemical microscopy is to analyze the interaction and the change of the current when you determine when you change the distance between the tip and the surface. So the response can be obtained depending upon the property of this surface. For example, here, if the tip in blue, when we have some conductive surface, when the distance between the tip and the surface decreases, one observes an increase of the current. In this case, we can speak about the positive feedback. On the other hand, if we have some insulating surface, when you decrease the distance between the tip and the surface, we obtain a decrease of the current. So by analyzing this kind of approach curve and by means of some calculation, it is possible to determine some kinetic parameters. So what we do in this work, we try to use scanning electrochemical microscopy to analyze not only the charging and discharging, but also to determine the kinetics during the lithiation and delithiation of iron phosphate. And to do this work, we choose two kinds of redox mediator. The first one, the ferrocene, and the second one, dibromopherrocene. The choice of this redox probe is due to the thermodynamical condition. And also the composition of the substrate, we have some mixture of lithium iron phosphate and iron phosphate. And in this case, we can control by changing the composition of the surface, we change the energy level of the surface. So by using some scanning electrochemical microscopy investigation, we obtain this kind of approach curve during the lithiation and dilation. And after that, we do some calculation. I have no time to explain in detail the calculation, but by means of this kind of calculation, we are able to determine some kinetic parameters. And we show that we observe some linear variation of the effective rate constant as a function of ratio of active materials. The second point we have shown also is that the kinetic of delithiation is higher than the kinetic of lithiation. We can explain this main difference due to the fact that during the lithiation, during this intercalation, we need more energy, and it explains the decrease of the rate constant. Okay, but now we try to go beyond. By using the same concept, the thing is that we want to use the same redox molecule to do both charging and discharging process. Before, to do charging and discharging, we need one couple for charging, another couple for discharging. And here we use some half cell, and here the idea is that we try to design some molecule able to not only to charge and discharge the iron phosphate, and the idea is to analyze what is the parameter that control the energy level at the interface. And here, by means of some thermodynamic analysis, we are able to show that the driving force at the interface depends upon of the ratio of the activity. So depends upon of the concentration of and the activity of iron, the oxidized form, and also the lithium ion. We are able to show that during the charging, since the oxidized form is formed, in this case, we have some movement of lithium and also some displacement of ion. During the same discharge process, we have the reverse system. So, for example, here we have designed this redox active ionic liquid. In this kind of ionic liquid, the cation bears some redox active system, for instance, here the ferrocene. And here, for example, by analyzing this kind of cyclic voltammetry, by analyzing this specific design of electrode interface, we show that, in fact, the presence, when you analyze, for example, that we have no contact, there are no Faraday current, we have this blue one. And now, if you have a redox active system, we have some increase of the current. This indicates that the charging and discharging take place at the interface. So now we use it in a cell, and we do some charging, discharging cycles. And as you can see here, for example, we can compare the charging and discharging process in the presence of lithium iron phosphate in the tank or not. And we can see here clearly that in the presence of lithium iron phosphate in the tank, we obtain we are able to store more energy. This result indicates that the concept works, and the same molecule can be used as charging molecule and discharging molecules. The second point is also that here the hysteresis is very low, and this low hysteresis is mainly due to the kinetic part. And here the most interesting thing is that we are able to obtain very high energy density compared to some vanadium redox flow battery. So to summarize this work, in fact, in this work we have shown that when you compare with other non-aqueous redox system, redox targeting redox flow, and as you can see here, for example, it is the system that we developed. What you observe, we observe very low hysteresis. In fact, the voltage loss is very low. And also, we have very high voltage of efficiency. Also, a large part of the solid materials are work during the charging and discharging. And this kind of system open different kind of application. Our idea is that, okay, during this work, we show that we validate the concept of a redox targeting system. And here, it is mainly driving some Nernst potential system. Also, we show that it is possible to use a single molecule redox targeting just with some simple composition. We don't need a very complex molecule. It's a very simple system. And now we try to do the same thing for aqueous redox battery. And to this end, we need to design a specific redox active molecule, but also to choose what kind of electromaterials are used. It is useful for this redox battery. Also, the idea is that to go beyond lithium-ion battery and use some materials that can be useful, for example, for sodium battery, also for potassium battery or proton battery. It is the idea. The thing is that we try to develop this new concept, and the idea is to go beyond. And here, I expect from application point of view, is that the most important thing is to be able to have some aqueous redox system. So just to finish, I would like to acknowledge some students and some researchers involved in this project. This project is a joint project with the group from Singapore, the group of Professor Chin Wang, and this work is supported by the alliance between Université Sorbonne Paris Cité and National Seoul University. And thank you very much for your attention.
Phosphate redox flow battery, what's the kind of energy density, gravimetric and volumetric are you looking at?
Okay. In fact, the thing is that here the idea is we need just to show if it is possible from kinetic and thermodynamic point of view. And now we have not optimized the system. I think that it is possible to go beyond. In fact, the idea is that if we are able, for example, to design some porous materials based on lithium iron phosphates, such as some granular, more compact materials in order to have some diffusion of redox targeting system. I think that we can obtain some not far from 80% or 19% of active materials. But in fact, here we have just to show the concept. Is it work or not, but it's not optimized because you must take into account of hydrodynamic and so on.